something about the Hermitian operator and unitary operators in here, quantum mechanics. Hermitian operator is very important in quantum mechanics. And the adjoint, or the Hermitian conjugate of this operator is equal to itself. So that is the Hermitian operator. And a Hermitian operator can be used to represent the observable. The observable is an item in quantum mechanics. It is a physical quantity, and it is represented by a linear Hermitian operator. And the observable is connected with the quantum measurement. And the quantum measurement is connected with the eigenvalue problem. Okay, eigenvalue problem is the equation of like this. And here, the Hn is the nth eigenvalue of this Hermitian operator H, and correspondingly, the Un cat is the eigencat, eigenstate, eigenvector of this Hermitian operator, corresponding to the eigenvalue Hn. Okay? And we know that, and we will prove today that Hn must be a real number. Okay? So that's for the Hermitian operator. We'll face the Hermitian operator every day in the future in quantum mechanics. And how many Hermitian operators do we have? We have the position, right? That's canonical position. Canonical what? Momentum. The angular momentum. The energy. The Hamiltonian. And also have the spin angular momentum and orbital angular momentum. And also have the parity. That's a very quantum item. In classical mechanics, we do not have the spin. We do not have the parity. And also we have some other Hermitian operators. For the identical particles, we have the transposition. Transposition is also a Hermitian operator. But also we have the permutation. But permutation is not the Hermitian operators. It is only a unitary operator. Okay, so that's a very brief summary of the Hermitian operators. And for unitary operator, we have the unitary operators in quantum mechanics. It's like this. Well, it's U dagger is equal to the inverse of the U operator. And correspondingly, or equivalently, U dagger U is equal to U dagger is equal to identity, right? But we should be very careful here about the unitary operators, because we will mention another thing that is called the anti-unitary operators. So we should, we have the psi prime that is transformed by U from psi. And also we have the phi prime is equal to U phi. And what do we have after the transformations by U operator? After transformation, we have the preservation of the inner product of the phi and psi. So that is phi prime. Psi prime is equal to that of phi and psi. So that means this transformation preserves the inner product. The inner product of arbitrary two-state vector in a Hilbert space are preserved, are kept to be invariant. Okay? So this is very important for the unitary operator. And we have a anti-unitary operator, which is a very special thing. The anti-unitary operator, A dagger, is also equal to A, the inverse of that. But what's the difference between the anti-unitary and unitary operators? We also have the transformations made by A, and psi prime is equal to this, A psi, and phi prime is equal to the A phi. But what is kept invariant? What is preserved? It's not the inner product, but the absolute value of the inner product of that. So we have the phi prime, psi prime. The absolute value of that is kept invariant. So that's the only difference between the unitary and anti-unitary operator. So like this, if you psi prime change to psi like this, and absolute value will be kept invariant, right? You just have exchanged the positions of the cat and ball, but the absolute value for the inner product is kept invariant. Got it? Okay. Okay, so that is the anti-unitary operator. Okay, this is a very special thing in quantum mechanics, and we have only one example for this. So that's not very frequently used stuff. Okay, let's see. For the unitary operator, what is the function for this operator? For the function of Hermitian operator, it is observable, right? And it can be used to represent the measurement of the quantum process. And the eigenvalue for this operator is real number. But for the unitary operator, it's this. It is for what? It is for some symmetry transformations. We have many kinds of symmetry transformations. We have several kinds of symmetry transformations. We have the discrete case. What kind of discrete case for the symmetry transformations? We have, for example, we have the space reflection. Okay, or it is called the space inversion. Or we can call this transformation as a parity transformation. Okay, this is a unitary transformation. And the conservation quantity for this transformation is the parity. Parity is a very, very special thing. And it is only valid for the quantum mechanics. You cannot see the conservation of the parity in the classical mechanics. And also we have another thing, that is transposition and permutation. And this transformation, permutation, transposition, is a transformation for the identical particles. And permutation is just a permutate. You can permutate any particles in an n-particle system. And transposition is only an exchange of the i's and j's particle, I to j and j to I. That's a very, very simple case for the permutation for the n-particle system. Okay, and transposition is a Hermitian operator, it's a unitary operator, and the involutory operator is a trinity operator, just as what I have mentioned last time. But the permutation operator is only a unitary operator. It's not the Hermitian, so it's not an involutory operator. Okay, got my points? And so this is for the identical particles. So this symmetry transformation is only a very special case in the quantum mechanics. It is not the classical mechanics phenomenon. And for the identical particles, we have the two cases. One is the symmetry. Symmetry. So that's boson. And also we have the anti-symmetry. That is the fermion. Okay, so we know that the space reflection or the parity operator is a unitary operator, and also it is a Hermitian operator. And transposition is a unitary operator, and also it is a Hermitian operator. So both these two guys are both the Hermitian and the unitary and involutory operators, the trinity operators. Got my point? Okay, so these two things are also connected with the observable. They are both the transformation and the observable, because they are both the Hermitian operators and unitary operators. We have very few cases for the trinity operators. Actually, we have altogether we have 3 cases for the trinity operators, for both the Hermitian and unitary operators. These are 2: parity, transposition, and Pauli operator. Altogether, we have 3 in quantum mechanics in this course. Okay? Okay, so this is a discrete case for the symmetry transformation. And also we have another kinds of symmetry transformation. That is the case for the continuous. That's a continuous case for that. And for the continuous, we have, it is connected with, it is connected with another thing. It is connected with the Lie group, of course, and also the Lie algebra, because the Lie group and Lie algebra are a very good tool to represent the symmetry transformations. And for the Lie algebra, we have a very key item, that is the generator. That's the generator for the Lie algebra. And for this, they are connected actually. We have several cases for the continuous case for the symmetry transformations. We have the time translation. Okay. Oh. And for the time translation, we got the conservation quantity, that is the energy, or Hamiltonian. Okay? So that is the conservation quantity for the time translation. And also we have the space translation. For the space translation, we have this conserved quantity that is called the momentum. Okay, and also we have the space rotation. Okay, for the space rotation, we have the angular momentum. And this is for the SO3 symmetry. And also for SO4 symmetry, we have another conservation quantity that is called the LRL vector. Or sometimes we call this vector as the length vector. Okay? And for the conservation of the angular momentum, you have the good quantum number as the L square or J square or something. So you have the degeneracy to be L square J square. But for LRL vector conservation or the length vector conservation, you have the N square. That is the N square means the principal quantum number square. Okay, N is the principal quantum number. And L and J are the orbital and the total angular quantum number. Okay, so actually what is the operators? The operators is just the Hamiltonian is the generator, the momentum is the generator, and also the angular momentum is the generator. So generator is the Hermitian operator. So the generator is used to generate a transformation. Right? It's just like the generating functions in the Hamiltonian mechanics. We have the canonical transformation, and canonical transformation is connected with the generating function for the type 1, 2, 3, and 4, right? So the generating function is used to generate the canonical transformation. And actually, in classical mechanics, the generating functions can be used to generate the time translation and space translation and whatever. And the conservation of momentum, energy, or something is connected with the generating function. And generating function is called the generator, of course. So the generator here is used to generate the unitary transformation. So you can see that the unitary transformation is generated by the generator, and generator is a Hermitian operator. So the generator is connected with this guy. So you can find that the Hermitian and unitary transformation, you have the Hermitian operator and the unitary operators are connected in this way. And at last, I would like to mention one more thing that is very quantum. That is the anti-unitary operator. The anti-unitary operator is what? We have only one case for this in quantum mechanics. That is called the symmetry. Of course, it is also a symmetry transformation. It is also a symmetry transformation for the discrete case. Okay. But now here, this and this are different because that symmetry is unitary and this symmetry is anti-unitary. And for the anti-unitary operator, you have an example of the time reversal. The time reversal transformation is also very important transformations in quantum mechanics. And even in the hydrogen atom, you can see the time reversal. It has nothing to do with the conservation of any physical quantity, but time reversal is connected with some very important quantum physical phenomenon. I have no space. It is something like Cramer's degeneracy and silver selection rule, the detailed balance theorem or something, and all the things are connected with the time reversal. And Cramer's degeneracy is a very special degeneracy that exists for some half-integer spin system. For example, for the hydrogen atom, you have only one electron. For the one electron, that means that the system is half-integer spin, right? Because you only have a 1/2. The spin is only 1/2. And of course, you have some other fermion systems. You have 3/2, 5/2 or something. That is also the half-integer spin system. And for that system, you can have the Cramer's degeneracy because you have the time reversal symmetry transformation. Okay, so let's summarize all of the things here. And Hermitian operator, it has a common points as a unitary operator because they are both a linear operator, and the unitary is linear operator, but the anti-unitary transformation is not linear. It is anti-linear. It is anti-linear. So what's the meaning of the linear and anti-linear? Let me give you some more explanations of that. So we can have some very brief introductions about what is the linear and what is the anti-linear. Well, linear means like this. If you have the H, you operate on the A psi 1 plus B psi 2. And then it will be equal to the A H psi 1 plus B psi H psi 2. So this is the linear. This is linear. And what is anti-linear? The anti-linear means you have the A operator that is the anti-linear operator. It operates on the A psi 1 plus B psi 2. What's the result? The result is different from the linear operator. That is A star A conjugate psi 1 plus B star A psi 2. So that is the anti-linear operator. So that's the difference between the linear and anti-linear operators. You can see that the only difference is only occur in the coefficients. One is kept the same, that is linear. Another thing is changed to the complex conjugate, that is anti-linear. Got it? So anti-linear and anti-unitary is connected. If you say that is anti-unitary, that means it must be anti-linear. It could not be the linear operators. Okay, altogether, all of the operators involved in quantum mechanics for this advanced quantum mechanics course, all of the operators are just here. Okay, let's come back. Okay, I just made a summary of the Hermitian operators, unitary operator, and anti-unitary operators, and also I emphasized the difference between the linear operations and the anti-linear operations. So I think that anti-linear something is very different, and it's just like some very special things. But in quantum mechanics, I think you don't need to worry too much about that because most of the cases will be focused on the linear cases. So the only exception for the anti-linear is a time reversal. So when we learn the time reversal, we can pay more attention about the anti-linear, anti-unitary something. But for the other cases, no anti-linear, no anti-unitaries. All of the things are just the unitary transformations, and everything is linear, so you can be very happy with that, right? And this table, this blackboard, I just finished this after lunch today. So, okay, let's discuss something about the something some more things about the eigenvalue problems. Eigenvalue problems. Eigenvalue, and of course, it is connected with the eigenstates, or the eigenvector, or the eigenket, or sometimes the eigenbron, right? And also for the eigenvalue, it is connected with another item that is called the spectrum. The spectrum. The spectrum is a very important item in quantum mechanics, and even before quantum mechanics, because you have the spectrum for the light, for the atom or something, right? And nowadays, spectrum is a very important technology for us to explore the universe. Okay, and normally for the eigenvalue problem, this is an operator, and the eigenvalue equation is like this. And this is for the discrete case, right? You have the discrete eigenvalues. And normally the value of n can be taken from 1, 2, 3, 4 up to n, and n, the capital N, can be chosen to be infinite or can be chosen to be finite. And also you have another case that is, you have this. And that is the continuous. This is a continuous spectrum. And this is the discrete spectrum. And for the continuous case, we have some difference in the conditions. For the discrete, we have the three things. We have the orthogonal, we have the normalization, we have the complete things. We should study these three conditions for the eigenstates. And so the first thing is the orthogonality. So this orthogonal and normalization are connected together. For the eigenvectors, for the discrete case, we have the psi n, psi m is equal to delta nm. And also we have a psi n, and this is the outer product, is equal to the identity. And this condition is the completeness of the basis. And now the eigenstates, the eigenvectors, eigenkets can be used as the basis of the Hilbert space. The basis. Okay? And this is called the also normality. There are two things. Also normality. You know that the delta nm is equal to 0 and 1, right? 0 means orthogonal. The basis of this are orthogonal to each other, or are perpendicular to each other. And for each basis, the length of that is equal to 1. It's a unit vector, so that is normalized. Okay, we can prove that later. And the completeness conditions for the basis of the eigenvectors, and this relation is also called the resolution of identity. It is called the resolution of the identity. And for the continuous case, it's very similar, but now the also normal condition for that is the A A prime is equal to the delta A minus A prime. So that is not normalized by the Kroneck delta, but the delta function, the Dirac delta functions. This is the contribution for the physicist. As I have mentioned that in Hilbert space, for the mathematics in Hilbert space, you do not have this, but for the physics, we have this. Okay? So this is the also normality. Okay, for that. So you have it is equal to 0, that is orthogonal. And also you have the infinity, that is normalized. Right? For the continuous case, you have the Dirac delta function. So the infinity means it's just like the unity for the discrete case. And for the completeness or the resolution of identity, it is defined by the integral instead of the summation of that. So you have the A cat, A bra, dA is equal to identity. So this is the completeness of the basis. And also, it is called the resolution of identity for this continuous case. Okay? Okay. So that's for both the discrete so this is for discrete case, and this is for the continuous case for the eigenvectors. So that means the eigenvectors or eigencats or eigenbras, eigenstates of any Hermitian operator. Keep in mind, Hermitian operator, the eigenstate of the Hermitian operators can be used to be the basis of the Hilbert space. Only the eigenstates of the Hermitian operators can be the basis of the Hilbert space. If you have some eigenstates for unitary operators, no, you cannot do that. Right? So this is for the Hermitian. Hermitian operator. If we have time today, maybe we'll prove some theorems for the eigenvalue, eigenstates of the Hermitian operators. But I would like to emphasize a very important concept here. For only the eigenstates of the Hermitian operators can be used to be the basis, not the other operators. Okay? Okay, that's what I want to say. And I would like to mention one more explanation of what's the meaning of eigen. The eigen. This is a German. It's a German word. We'll learn several German words in this course, in this semester. Not only the eigen, but also because we have a Wigner D matrix, and a D it's a Dreitung something, that is also German words. Because many contributions in quantum mechanics come from German people, or the people who can speak German. Austrian people, German people, Hungarian people, they speak German, and so they invented some new things and termed as a German word. Okay, and the meaning for this eigen means that proper or characteristic. Actually, I think that in linear algebra, you have learned in the first year, right, as an undergraduate student. The translation in linear algebra for the eigenvalue is called the, like this, right? In linear algebra. So that is characteristic. And proper means that is correct, that is very appropriate. So eigenvalue, eigenstates, eigenfunctions, eigencat, eigenbros, eigenthis, and eigenthat just means this. Okay, got my point? And some more things that about the state vector. I want to mention one more point about the state vector. For the state vector, we have the psi is a state vector, of course. If you have just simply you have the c psi and ei theta psi, what will happen? What's the relation between this vector, and this vector? Mathematically speaking, they are equivalent. So this means in mathematics it is called equivalence. It is also a relations. It is not equal. It's not identical. It is equivalent. But in physics, if you have several vectors to be equivalent to each other, that means the same. So for the physics, we say that they are equal. So psi is just like this vector, right? This is a vector. And what is c psi? If in the real number, if c is a real number, that means you only have you only enlarge or shorten the length of the vector, but the direction is kept invariant, right? So maybe this is a c psi, and ei theta psi in the complex, for the complex number in the Hilbert space, because Hilbert space is a complex number state, right? It's not like the Euclidean space is for the real number, but for the Hilbert space, that's for the complex number. So you only have a global phase factor here. This is called the global phase. That's called the global phase. It doesn't mean anything in physics. It cannot cause the difference. So we'll see that the psi is equal to the psi c psi over this c psi, and it's equal to psi e to the minus I theta psi right? So that means all the three representations are the same for the same vector. And so along this ray, along this direction, we say that it is a vector space, of course. It's a state vector space. And also, it can be any long with the same direction. And this is called the ray space. And the vector can be called the ray vector. So we don't care about the magnitude of that vector. We only care about the direction of this vector. And so we can choose to normalize each vector, because in quantum mechanics, the normalization is required for the vectors, for the simplification, for the calculations for any systems. You got my point? So anyway, that's the same. The psi is the same as the c psi, as the I theta psi. So they are along the same ray and they are in the same direction, so they are the same vector. But we have another case, because we have the A, if it operates on this, if psi ni is not equivalent to psi nj, and I is not equal to j. That means the psi j or psi I cannot only have the difference in the global phase or some coefficient here. They are more different. They are more different. So they are not the same. In this case, we call that it is a degenerate. That is degenerate. If you have this eigenvector, and also you have this eigenvector and this eigenvector, that's the same eigenvector. That's the same eigenvalue correspond to the same eigenvector. You don't have any degeneracy. That is non-degenerate. But in this case, if you have this case, you have the same eigenvalue but with a different eigenstate. Because the psi ni and psi nj with the different I and j value, they are not equivalent. That means they are not equal to each other. That means the same eigenvalue corresponds to different eigenstates. This case is called the degenerate case, or the degenerate eigenvalue problems. So that is what we discuss today. And normally for this, the I is equal to 1, 2, Gn. It is connected with the value of n because the eigenvalue here, you have the index of n. And what is the value of n? N can be taken to be 1, 2. Suppose that you have altogether, you have the capital N values. Okay? And for this, and then you have the concept of the subspace. It's a subspace for the Hilbert space. For each eigenvalue, you have this. It corresponds to the nth subspace. And for all the values that you can take for the whole Hilbert space, you will have this relation. Oh. And each index here represents, it corresponds to the index of your eigenvalue. Okay? But for each eigenvalue, you may have several eigenstates. If one eigenvalue corresponds to one eigenstate, that means it is not degenerate. But if you have one eigenvalue but several corresponding eigenstates, that means it is degenerate. For the non-degenerate case, the dimension of that subspace is only one-dimensional. But for the degenerate case, the dimension for each subspace is Gn dimensional. And so the total Hilbert space for your eigenspace is equal to 1 right? Because this is equal to the whole Hilbert space, right? And this is equal to the and for each subspace, what is the dimension for that? The dimension is determined by the degeneracy for each subspace. Okay, you got these expressions already? I think it's very easy to be understood here, right? Okay, so, and the subspace corresponds to the nth eigenvalue is defined as this. This is the vector for this subspace. And I is equal to 1, 2, Gn. And Gn is the degeneracy of this subspace. And n is equal to 1, 2 to capital N. The capital N is the total number for the eigenvalue, right? And Gn is the total value for the eigenstates correspond to the nth eigenvalue. Okay? Okay, so this is a very important result that you can derive here. And for the degenerate case, we have the orthonormality conditions. It's like this. It is equal to delta n, n prime, delta I prime. And the value is the n prime is equal to 1, 2, up to capital N, and the I is equal to 1, 2, Gn. And I prime is equal to 1, 2, and dot, 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 up to G n prime. So I think that you can understand this. Okay, so we can take a break. Many students ask me some very common questions, such as the linear and antilinear. Here, I just want to say something more about this. Remember, keep in mind that the linear is very important item for the vector space, and for any vector space it is also called the linear space. So linear and vector are connected together. So the vector is linear, of course, but in a linear space you can have some not linear things. For example, the operator. You can have the antilinear operator. It can live in the linear space, no problem. But the vectors is linear. But operator do not necessarily to be linear. Okay, got my point? There are more, I think there are many discussions we can discuss later about this, because there are many things that is very conceptual, and that's not very easy to be discussed in just one sentence. Okay? But keep in mind that in the Hilbert space is a linear space. It is a vector space. It is the inner product space. So the vectors here, in all of the Hilbert space, it must be linear. But the operators can also live in the Hilbert space. But the operator do not necessarily to be linear. It could be linear, and also it could be the antilinear. Okay? Got this point? That's okay. Okay, so I have finished almost all of the eigen stuff, and I would like to generalize about the orthonormality and completeness. So if you have the discrete spectrum, you can write down the conditions of that. And also for the continuous, you can write down the similar things. But for the mixed spectrum, what will happen? For the mixed spectrum, you will face those mixed spectrum every day, because for this hydrogen atom, it is a mixed spectrum, right? When the hydrogen atom is a bounded state, it is discrete. But the electrons in the hydrogen could be excited to some very high energy level, and up to the free particle. And so for the hydrogen atom, it is a mixed spectrum for both the discrete and continuous spectrum. Okay? And for this, if we have the spectrum for the hydrogen atom, the hydrogen atom, this is the ground state. That is minus 13.6 electron volts, right? That is the ground state energy. And then you have the 1 over n squared of the bounded state eigenvalue, right? So it's like this. It is discrete for the bounded state. But after 13.6 electron volts, the electrons can be excited to some critical point, and then it becomes a free particle. So after that, the atom will be such a particle. It's a free particle. So in this region, it is the bounded state. The bounded state is discrete. But for the free, it's an unbounded state. It's a free particle. The energy will be continuous. Okay? So it's a mixed spectrum for both the discrete and continuous. And so for this, you have the also normality condition is like this. It should be like psi n, psi m is equal to actually, because this case is a degenerate case. So we have for the hydrogen atom, as an example, that is the n, l, m, n prime, l prime, m prime is equal to something. That is delta n, n prime, delta m, l, l prime, and delta m, m prime. And that is also normality conditions for the hydrogen atom. For the discrete case, this is for the discrete case, right? And also for the unbounded state, that is a free particle case, that is continuous. So what do you have? You have E, L, M, E prime, L prime, M prime. You don't have the principal quantum number here any longer for the continuous case. And you have, for the continuous spectrum, you have this. That is a delta function here. It's a delta E minus E prime. That is not the delta E prime. That is not discrete any longer here. It's a continuous version. But for the angular quantum number, you also have the delta L prime and M prime. And this is for the continuous case for that. So also normality, you have the two altogether for the hydrogen atom because it is a mixed spectrum. And also for the resolution of identity, what's that? The resolution of identity, you have the discrete and continuous together. What's that? What is the discrete? Discrete is NLM here. That is NLM NLM plus. This is completely a discrete case, right? And also we have a mixed case for what? we have another mixed state that is but and altogether you have the identity. This is the identity. So this relation is discrete plus continuous. For what? Because for the energy, it is continuous. But for the angular momentum, it is not. You also have the eigenvalue problems even in the continuous. For the free particle case, you have the discrete case for the eigenvalues for the angular momentum. So this is kept to be discrete. But for the energy here, it is continuous. Okay, keep in mind, this is very important. Okay. Well, I would like to mention one more thing about the unitary operators for its eigenvalue problem, because we have discussed many things about the eigenvalue problem for the Hermitian operators now. Now let's turn to the study about the eigenvalue problems for the unitary operators. Eigenvalue for unitary operator. Unitary operator. We can assume that the U operate on this state, and then you have this. So the small a here is the eigenvalue, and this a cat is its eigenstate, right? So what will happen? Starting from this, you will have the a u dagger is equal to a star a here, right? Okay, so you can have a u dagger u a is equal to what? This and this. So you can get the a square, the absolute value of a square, right? This is one of the expressions that you can derive. But what is this? Because u is a unitary operator, so u dagger u is equal to identity. So here it means it is equal to the bra a and cat a. So these two things are the same. So that means it's a square of the absolute value of a is equal to 1 to the unity. So that means a is equal to this. So this is a theorem for the eigenvalue for the unitary operator. The eigenvalue for the unitary operator must be a complex number. A is a complex number, right? A is belongs to the complex number with the what? The absolute value of A should be unity. Okay, so you can have a unit circle in a plane, and that is the value of the eigenvalues for the unitary operators in the complex plane. Okay, you got? Yes? Okay, good. So let's deduce something that is very interesting. From that result, we know that UA is equal to EI theta A, right? And so, what can you derive from this? You can derive A U dagger is equal to E to the minus I theta A bra. Okay? It's very simple. So after this, you can have a multiplication from the right-hand side of u to this both sides of this equation. And what will happen after that? You will have the a brawn u dagger u is equal to e to the minus I theta a u, right? And this is equal to 1. That is identity. So you can have this is e to the minus I theta a u. So you can have the e I theta a brawn is equal to a brawn u. So what can you derive from that? You can have, if you have take the dagger to both sides, and then you have u dagger a is equal to e to the minus I theta. So you compare with u a is equal to e to the I theta a. Right. What can you get from that? You can find for the u or u dagger, they have the same what? You have the same eigenstate, but with a different eigenvalue. So this is the eigenstate of u dagger, and this is also the eigenvalue of u. Okay, so this kinds of calculations is very important for the unitary operators. So you should keep in mind about all of the procedures, some of the tricks, the techniques used in these calculations. Okay. Okay, I think that I finished about the something about the unitary operators, and now I would like to introduce our very important some theorems of the Hermitian operators, because Hermitian operators, I think it's more important. The theorems related to the Hermitian operators. The first thing is that the eigenvalue of the Hermitian operator is what? Is real. That's very important. And the second is that the eigenstate of the Hermitian operators is or must be what? Must be two cases. One case is orthogonal. That's one case. The eigenstates, the eigenvectors of the Hermitian operators must be orthogonal. Or, then, so this case is for the non-degenerate. For the non-degenerate eigenvalue, it must be orthogonal. For the degenerate case for the Hermitian operators, what will happen? Must be able to be made to be orthogonal. That is for the degenerate case. If you have the degenerate eigenvalue for the Hermitian operators, you can have several degenerate eigenstates, right? They are not necessarily to be orthogonal, but you can make them orthogonal by some way. And that method to make these eigenstates to be orthogonal is called this method is called the Gram-Schmidt also normalization. Also normalizations. That means you have two things to do. You should make them orthogonal, and together you should make them normalized. It's very easy to make something normalized by just dividing something, right? That's very simple. And to make the things to be orthogonal is a little bit complicated. And I will introduce how to make some things orthogonal. And after I give you some introduction about this method, you will see that it's very simple. It's very straightforward. If you have learned the geometry before, you will see that it's so simple. Okay? So let's see the first thing. Let's see the first thing. I think that for the Hermitian operator, it's very easy to prove that the eigenvalues to be the real number. And this is a homework. And I think maybe after several equal days, and then you get results. So I will not prove it here. And for the orthogonal, for the non-degenerate case, it is also very simple. Actually, these two things, real eigenvalue and orthogonal eigenstates for the non-degenerate case, both things can be proved together at the same time. It's very, very, very easy. And I have given you the proof in the lecture notes. So I think that you can do that yourself. So this is homework, of course, you can do that. And I would like to spend some time to discuss something about this Gram-Schmidt also normalizations method. So it is abbreviated as the GSO. This method is called the GSO. If I draw a picture for you, and then you can understand the idea of GSO is very simple. All right, this is something like this. We have the X and Y. I have told you that A psi n I is equal to A n psi n I, right? So that means you have so many different eigenstates. The eigenstates psi ni is not equal to psi nj, of course. If they are equal to each other or equivalent to each other, that means the only difference between these two vectors is only a coefficient or a global phase, right? And in that case, that means the two vectors are in the same ray. What does it mean in a linear algebra? This is called the linearly dependent. This is called the linearly dependent. But if they are not equal to each other or they are not equivalent to each other, that means they are not linearly dependent. That means they are linearly independent. It's just like this. This is a V1, that is a vector, and this is V2, right? That's another vector. If the V2 and V1 are not in the same direction, these two vectors are linearly independent. Linearly independent vectors are not necessarily to be orthogonal or perpendicular to each other, right? They are just, you just require that they are linearly independent. That's enough. They are not necessary to be orthogonal. That means they are not necessary to be perpendicular to each other. You just require that they are not in the same direction. That's enough. Okay, got my point? Okay, give me some response, okay? I'm also very exhausted. Okay, provided that these two vectors are not in the same direction, you can do that using the GSO. You can make these vectors to be perpendicular to V1. How to do that? You can make this, right? You can have a projection in this direction, and then you get the V2 prime. And V2 prime now is perpendicular to V1. So the V1 and V2 new basis orthogonal. That's the basic idea for the Gram-Schmidt. That's it. It's just so simple. And how to do that? Let me show you that. The first thing, you have the step 1, because you have the psi n1, right? That is your first eigenstates corresponding to the nth eigenvalue. You want to make it to be normalized. Okay. The normalization is very simply made by right? This is the normalizations. It's so simple. Okay, so now these vectors here can be the basis. It is a normalized basis. The second step is you want to have the psi, you want to have this. And then this minus this is equal to this, right? Okay, so from psi n1 you can have the this thing is psi n2. What is psi n2? This is psi n2, right? Minus what? Minus this component, the parallel component of that. And what is the parallel component of that? It is this projection to this axis first. You have a psi, yes, psi n1, psi phi n1 and psi n2. And this psi n1, right? It's just like this. V2 minus what? Minus this. X0 V2. And this is the projection, the component of this. And then you have a unit vector. The unit vector is this. Right? Got my point? This is x0, right? This is the x0. That is the unit vector for the x-axis. Understand? And then you got such a vector. This vector is this. But this vector has not yet been normalized. So the third step, make this thing normalized. How to make it? The normalization is the same as this. You have the chi n2 and over bra chi n2, chi n2. So you got the normalized vector for this. That's the second eigenstate. This is the first, this is the second. And how to derive the third one? Similarly, you can just cyclically use the same method, and you can get all of the orthogonal bases. You can starting from the psi n1, n2, n3, ngn, and you can derive the phi n1, phi n2, phi up to phi ngn, right? And you do it. You can get the phi n1, phi n2, phi n. How many do you have? You have gn, because the degeneracy is gn for the nth eigenvalue for that. Okay, well, that's the very brief, but I think the key points of the Gram-Schmidt also normalizations method. And the name is very complicated because the Gram-Schmidt and also normalization, and it looks very complicated, but actually it's very simple. If you have such a picture of that vector's decomposition, you have the parallel component, you have the perpendicular component, and then you got it done, right? Do you have any problems? I think that I finished all of the almost all of the lectures that I would like to give you today, and now we have about 5 to 10 minutes left, and we may discuss. If you have problems, you can raise your questions. By raising your hand, you can do that, or maybe after class we can discuss something about it. Okay, so any questions? If you do not have any questions, the time is up and it is over for today. And thank you.